Hi, I'm Ramid Mojab, and in this video I'm going to talk about an event in probability theory. This is the first session of a more general program on statistics and econometrics. Let me summarize the main points first. I'm going to talk about the sample space of an experiment. It's a set and we are going to use set theory. I'm also going to talk about Sigma Algebra on the sample space. It's a subset of the power set of the sample space, and it indicates the level of available or required information, and we'll use it as a tool to exclude irrelevant information. In this regard, I'm going to introduce the concept of generated Sigma algebra. And if you're familiar with macroeconomics and rational expectation, you might find it useful because later we will use it to define the conditional expectation. And an event, I'm going to define an event. An event in an experiment is a member of the Sigma algebra that is defined on the sample space of the experiment. Our discussion starts by defining an experiment. A random experiment is a procedure that is partially under control. Since we are not concerned with deterministic experiments, we simply say an experiment and we omit this word. Every experiment has a well-defined set of possible outcomes, and we call it sample space. I use omega to denote it, and each member of omega, or the sample space, is an elementary outcome. Here W is an elementary outcome because it's a member of omega, and one of the elementary outcomes will be obtained in every experiment. And there are three types of sample spaces. A sample space is whether countable and finite, countable and infinite, and uncountable. A countable and finite sample space is a discrete sample space. For example, when in an experiment, when a dice is tossed, we have a discrete sample space. A sample space that is countable and infinite, it's an infinite discrete sample space. Compare these two names. And when we select a random natural number, we have an infinite discrete sample space, and an uncountable sample space is continuous sample space. And when we select a random real number, we have a continuous sample space. Let's consider an example. There are three types of sample spaces, and I'm going to give an example for each one of them. For the discrete case, consider an experiment in which a dice is tossed. Omega is a set of 1, 2, 3, 4, 5, and 6. You must be familiar with this one. Must we use numbers in this set? The answer is no. We can, for example, use dots. And for example, here 6 dots. Later, we'll introduce the concept of random variable, and we can interpret these 6 dots to be 6. For the continuous case, consider an experiment in which a random real number is selected between -1 and 1. Omega is x, such that x is real and x belongs to this interval, -1 and 1. Okay, for the infinite discrete case, consider an experiment in which a natural number is selected randomly. Omega is similar to the omega in the discrete case, 1, 2, 3, and so on. It's an infinite set. Okay, if you remember from the elementary statistics, we are generally, especially in the discrete case, we are generally concerned with the power set. I use this sign to denote it. It's a big set. It's a big set of the subsets of omega. Okay, we know that A, for example, 1, 3, and 5 is a member of this power set. All members of the power set in the discrete case are events. This is an event in which 1 or 3 or 5 is obtained when we toss a dice. Okay, here in the continuous case, I'm not going to talk about the power set of the set. However, we know that A x such that x belongs to this interval 0 and 1. This is an event. I will talk about the probability of these events later. For the infinite discrete case, again, I'm not going to write down the power set. However, this set x such that x is even, this is an event. And we can talk about its probability. Okay, for the discrete case, you must be familiar with this formula. We can count the number of elements, therefore we can say that the probability of A is the number of elements of A over the number of elements of omega. This is 3, this is 6, therefore the probability of A is 1/2. For the continuous case, we cannot count anything. However, we can calculate the length. These are intervals. The sample space is an interval. We can calculate their length. The probability of A is the length of A over the length of the omega. The length of A is 1 minus 0. The length of omega is 1 minus minus 1. And it is 1/2. The difference between these two is that here all members, for the discrete case, all members of the power set are events. But this is not true for the continuous case. I will talk about it later. All members of the power set here are not events. Okay, for the infinite discrete case, things are a little more complicated here. Although we can count the number of elements, we cannot use this formula. Again, I will talk about this later in order to show that, for example, the probability of A, that we select a natural number randomly and this number is an even number, is 1/2. If we want to show this, we should use an asymptotic version of this formula here. I will talk about it in the next session. I have an exercise for you. This is similar to the discrete case of the previous example. We have an experiment here in which 2 fair coins are tossed. I want you to write down its sample space and calculate the probability that 2 heads are obtained. You know that the omega is similar to this one, H, T, and so on. H means the first one is head and the second one is also head. And note that H is an event, and we can calculate. I want you to calculate the event of the probability of this event. Also note that we are talking about an event in this exercise and the previous example. However, this is because we are dealing with discrete sample spaces, and for the general case we need to provide a more exact definition. That's why, for example, in the next slide I'm going to introduce the concept of Sigma Algebra. In order to continue the discussion, we should talk about this concept, Sigma Algebra. A set such as sigma is a Sigma algebra on a set omega if and only if sigma is a subset of the power set of omega. The empty set is in sigma. It's closed under complementation, which means if E is in sigma, then so is its complement. and it's closed under countable unions, which means if E1, E2, E3, and so on are in sigma, so is their unions. This property, the last property, describes a type of convergence. Here is a more familiar one. You must be familiar with this summation, and it is if r is less, or if the absolute value of r is less than 1, then it converges to this value, which is a member of R. We have similar membership here, and if it's not the absolute value is greater than 1, then it diverges, which means the value is not a member of R. I'm going to interpret sigma as the level of information. Later I will introduce the concept of random process, and there this interpretation is going to make more sense. In this regard, I have an exercise for you. I want you to show that a sigma algebra is closed under countable number of intersections. The last axiom was unions, closed under countable number of unions. Here, if EI is a member of sigma, I want you to show that their unions is also a member of sigma. You can use one of the De Morgan's laws, this one. Let's consider an example. In an experiment at dice is tossed, we know that the sample space is set of 1, 2, 3, 4, 5, and 6. We want to write down the smallest possible sigma algebra. We know from the second axiom that the empty set is a member of every sigma algebra, therefore it must be here. Its complement is omega, therefore it must be a member too. Their union is omega, which is already a member, and that's it. It is known as the trivial sigma algebra. It has two members. Here we have an extra member. Its complement is 1, 2, 4, 5, and 6. Their union is omega, which is a member, and you can check that all other axioms are true here, therefore it's a sigma algebra. Here we have two extra members. The complement of the first one is 1, 2, 4, and 6, and the complement of this one is 1, 2, 3, 5, and 6. The union of these two must be a member too. Therefore, we have 3 and 4. The complement of this one must be a member. Therefore, we have 1, 2, 5, and 6. And you can check that all the axioms are true here. Therefore, sigma 2 is a sigma algebra. The largest possible sigma algebra is the power set. Okay, I said that I'm going to interpret a sigma algebra as the level of information. What does this mean? If the level of information is sigma 2 here, I mean this one, this means that we cannot count the number of elements of this set because it's not a member of sigma 2. You might say no information available, or we do not have enough information, or E as a member of sigma 2 is undefined. Let's consider an example. And the left side of this equality is a sigma algebra. I'll explain this notation later. We want to complete the right side such that this is a sigma algebra too. If this is phi and this is omega, then we can close the brackets and it's the trivial sigma algebra. However, let's consider the general case. We must have phi and omega here, the union of these two, and the complement of these two. Also, we should have the complement of each of these sets and their union, and also the complement of this one, which is the intersection of these two sets. We should have, for example, the union of this one and this one, which is this set, and its complement, which is this one. And we should have the union of this one and this one, which is this set, and its union is this set. And I think that's it, and you can check that all the axioms are true for the right side, all the axioms of the definition. Therefore, it's a sigma algebra. Let's address an important question. Why don't we use the power set instead of all our sigma algebras? And we know that a power set is the biggest sigma algebra and it has all the required information. One might say that power set is generally big and complicated. We might not need all its members, or in other words, it has irrelevant information. A power set has irrelevant information. Of course, we know that sigma algebras might also be big and complicated. For example, you can try to complete the right side of this equality similar to the previous example. It's going to be a hard job to do. Maybe a better answer is that the concept of sigma algebra gives us a tool with which we can remove irrelevant information. This tool is the generated sigma algebra. A sigma algebra such as sigma of H, in which H is a collection of sets, is called the generated sigma algebra by H, by the collection, if and only if it's the smallest sigma algebra that contains all the sets. In the previous example, we actually generated a sigma algebra by a collection of two sets. Here, you can generate a sigma algebra by a collection of three sets. That set is the smallest sigma algebra that contains these E, F, and G. This is the example that we did before. It's a generated sigma algebra by this collection, and the answer is the same. The sigma algebra that is generated by this collection is the trivial sigma algebra. Sigma algebra that is generated by this one is also the trivial sigma algebra, and the same is true here. It's the trivial sigma algebra. If omega is a set of 1 and 2, then the generated sigma algebra by this collection, it must have 1, a set of 1, its complement, their union, and we know that all sigma algebras have empty set, and all axioms are true. You can check it. Note the notation that I used. I didn't use this notation. I used two brackets because I wanted to construct a collection of sets. The same is true here. This is a set, but this one is a collection of sets. Therefore, by definition, it's better to use this one. I have an exercise for you. Explain why the intersection of multiple sigma algebras is also a sigma algebra. Also, show that this is not generally true for the union of two sigma algebras. For the first part, verify the axioms of the definition. For example, if E is a member of the intersection, then it must be a member of all sigma algebras. Then its complement must be a member of all sigma algebras, and therefore its complement is in the intersection. For the second part, you can provide a counterexample. Now we want to define an event. As usual, let omega be a sample space in an experiment, and let sigma be a sigma algebra on omega. Every member of the sigma algebra is called an event. An event occurs if and only if one of its elements is obtained in the experiment. You should remember the definition of the experiment. There we said that an elementary outcome will be obtained in the experiment. If that elementary outcome is a member of one of these events, one or more than one of these events, we say that that event has occurred. Consider an example in which a dice is tossed, and let this set be the Sigma algebra. The first element, the empty set, is an event. It's a situation in which no outcome or no elementary outcome has occurred. We know that this is impossible by the definition of the experiment. Omega is also an event. It's a situation that something happens and an elementary outcome is obtained, and by the definition we know that it is certain. This one, the third member, is also an event. It's an event that an odd number is obtained in the experiment, and the last one is an event that an even number is obtained in the experiment. If 2 is obtained, an elementary outcome 2 is an elementary outcome is obtained, both this event and omega occur. Here we have 3 definitions, and after that 3 propositions. Let E and F be 2 events. We say that E is an impossible event if and only if it never occurs. E is a certain event if and only if it always occurs. And E and F are separate events if and only if they do not occur simultaneously. And also we can say that E is an impossible event if and only if E is the empty set. The proof is simple. For example, if E is the empty set and W is obtained, then W is not in E, therefore E never occurs and E is impossible. On the other hand, if E is impossible and E is not the empty set, there is a W that might occur which is in E, therefore E might occur, and therefore E is not impossible, which contradicts this assumption. The second one is E is a certain event if and only if E is the omega or the sample space. The proof is similar to this one. And here E and F are separate events if and only if their intersection is empty. Again, the proof is simple, and I leave it as an exercise. We can use set theory and prove some more propositions. Let E and F be 2 events. E occurs if and only if its complement does not occur. It's easy to explain this or to prove this. For example, you can use Venn diagram. Here this is E and this part is its complement. If W is in E here, we know that W is not in its complement. Therefore, if E occurs, we are sure that its complement does not occur. Here we say that the union of 2 events occurs if and only if one of them occurs. The intersection occurs if and only if both occur. The difference occurs if and only if the first one occurs and the second one, here F, does not occur. If F is a subset of E, we can say that E occurs whenever F occurs. Or if F and E are equal, we can say that E occurs whenever F occurs and F occurs whenever E occurs. It's easy to explain these propositions or to prove them. I leave it as an exercise. We have another exercise here. I want you to show that these equalities are valid. You can use Venn diagram or some other means. Here, explain what is the required level of information for impossible and certain events. And here, explain what is the required level of information for this collection of events. We did an example before, and you can use that one. Thanks for your time. In the next session, I will talk about probability function. Please note that I'm still learning statistics and any comment is appreciated.